Hello, welcome ladies and gentlemen to this interstellar journey. This is your pilot Mithil Sai Jakka. Today we are going to traverse the cosmos, uncovering the secrets of the exoplanet, shall we? Now before we blast off, let's have a glimpse of our exciting expedition, shall we? Okay, we will be having some introduction and we will be having a recipe or the formula and we will be having our solution or the conclusion for it. Now let's dive into it. The introduction part. Now, what are the exoplanets really? Now, imagine that you are a regent, a kind of alien species living on the planet G, a planet from the glacial solar system, which is circling or surrounding through the glacial star. So this thing it came from the movie Battleship. Okay, like where we send our signal to the Landsat 7 through the glacial solar system, to find any existence of an extraterrestrial beings living over there. But that part, those kind of planets in that movie is like from Battleship, Avatar, Star Wars. They really exist, and they're called the exoplanets. Okay, so the planets which have habitable environments in them, and they are typically out of our solar system. They are called as an exoplanets. So in order to find out these exoplanets, like which have the perfect conditions for a life to exist, like not too far from the sun, not too close to the sun, like too close it's too hot, too far it's too cold and freezing temperatures out there. So in order to find these exoplanets, or to pinpoint them, we're gonna have to look at the transit times of the exoplanets. So let's consider the transit times of the exoplanet, like the journey of the planet around its star. So the transit times, the period when these planets crosses their stars, are like just timestamps in this cosmic passport. They help us understand the exoplanet's size, orbit, and much more details about the planets, like maybe it's sustainable for a life like humans or maybe others to but there is a problem here, that a big black hole size problem. Calculating the transit times is more complicated. Like if you are trying to hit a moving target light years away, the transit times are not constant. Like the distance between two cities are not, like New York and San Francisco, maybe 1,000 miles or more. They vary due to numerous factors such as the planet's orbital speed, its distance from the star's size. This makes predicting times a complex task. There comes our hero, Mr. Dijkstra. I'm sorry if I spelled his name incorrectly. So our Dijkstra has invented an algorithm. So we are going to use it typically to predict these times. So he's a Dutch scientist. So this algorithm is typical like a pathfinding algorithm used to determine the shortest path between the nodes in the graph. Okay, everyone knows graph, right? Who doesn't know graph here? Please raise your hand. I'm just kidding. The nodes in the graph represents, let's consider it represents cities connected by the roads to routers in a network. In our context, come back to the context, imagine each exoplanet as a node and the connections between them as edges. The distance here would be the transit times. It starts from a single node and expands outwards. Always choosing the node with the shortest known distance thus ensures an optimalist solution. Okay, but we have another problem. We can't just directly implement this algorithm to our our problem. Then there comes Mithil's touch. That means your pilot's touch. So I have modified this traditional algorithm, the Dijkstra's algorithm, to adapt to the various transit timings. So instead of treating the transit times as constant, I incorporate a time-dependent function. This function typically considers various factors influencing transit times, allowing our algorithm to make dynamic predictions. It think this algorithm was now has a built-in crystal ball that adjusts dynamically its calculations based on the challenging or changing celestial conditions. Now after this modification comes our real thing, the implementation. Now I have tested our algorithm, the modified one, on the synthetic data, simulating a network of exoplanets using our time-dependent function. I predicted the transit times between these exoplanets. It's like aliens playing a cosmic game of connecting dots, but these dots are moving and the lines keep changing. As I said, the planets are revolving around the star, and the star is revolving around the in the galaxies and stuff. Yeah. And then with our implementation of this modified algorithm, now we're gonna see or look at some results by launching our algorithm. And voila, the results were promising. My modified algorithm was not only able to find or accurately predict the dynamic transit times, but also successfully determine the shortest paths between these moving celestial bodies. I found that our algorithm could navigate the complexities of our changing cosmic maze, much like that aliens would need to do when they chart a course through the stars. And finally, there comes our conclusion. Our journey concludes here, but the exploration doesn't end. There are countless exoplanets waiting to reveal their secrets, what kind of extraterrestrial lives they hold on, and what kind of things they are up to. With our tools like our modified algorithm, I'm sorry, we were one step closer to unraveling these cosmic mysteries. But there is always a catch. Although the results are encouraging, the universe is vast and complex. I need to test our algorithm on a larger scale and factor in more variables such as gravitational forces from nearby celestial bodies, effects of dark matter, and even potential anomalies in space-time. It's like adding new rules to our cosmic game of connecting dots. And the same phrase that I usually mention in our slide. Every new factor we consider brings us a step closer to understanding how our hypothetical alien friends might traverse the cosmic, or how we could traverse to the cosmic. Anyway, thank you guys, thank you ladies and gentlemen for joining us on this interstellar mission. Until next time, keep looking up. Signing off.